Okay, in this video, we're going to graph, given f of x, we're going to graph g of x using transformations here. So to do that, we're going to have to figure out the transformations. We'll use our rule inside x opposite, outside y same. So see x minus 1 inside. So we're going to do x plus 1 instead. Outside y is same, so we have two things outside. We got the negative sign and the plus 2. Negative sign means times negative 1. So we are going to do y times negative 1 plus 2. Now that we have our rule, we can start with our order pairs. Negative 2, negative 1. 0, 2, and 2, 1. We just have to apply our rule to these order pairs. Go down and do all the x rules first, which is just adding 1. So negative 2 plus 1 is negative 1. 0 plus 1 is 1. And 2 plus 1 is 3. And for the y rule, doing times negative 1, then plus 2. Negative 1 times negative 1 is 1, plus 2 is 3. 2 times negative 1 is negative 2, plus 2 is 0. And 1 times negative 1 is negative 1, plus 2 is 1. Now we just have to graph this. Negative 1, 3, 0, 1, and 3, 1. I think I have a point in the wrong spot here. So let's just double check. 1, 0. Place this point in the wrong spot. I did 0, 1. 1, 0. There we go. And there we have it. In this example, we're going to graph f of x equal to 3 times the absolute value of x plus 2. And on the outside, we have minus 3. So using our transformation rule inside x opposite, we're going to be doing x minus 2. And outside y same. Two things on the outside. We're going to do y times 3 and minus 3. Since this is an absolute value function, we're going to use the points negative 1, 1, 0, 0, and 1, 1. We'll apply our transformations. We're going to subtract 2 from the x values. Negative 1 minus 2 is negative 3. 0 minus 2 is negative 2. And 1 minus 2 is negative 1. For y, we'll multiply by 3, then subtract 3. So 1 times 3 is 3, minus 3 is 0. 0 times 3 is 0, minus 3 is negative 3. 1 times 3 is 3, minus 3 is 0. So these are our 3 new points that we'll use to help us graph. Negative 3, 0, negative 2, negative 3, and then negative 1, 0. We'll draw the shape in. There we go. You can also do this by just using this order pair here. And as a shortcut, normally the absolute value function goes over 1 and then up 1. However, this will go over 1 and up 3 in both directions because we have a vertical dilation of 3 due to the multiplication on the outside. So, yeah. In this example, we're asked to write the equation for the function graph below. We have an absolute value function graphed, so to do this, we're going to have to figure out the transformations first. Normally, this is the absolute value graph. So let's look at the vertex here. See how it's been moved around. You can see that's been moved up 3 into the right 1. So that means as far as the rules are concerned, we are adding 3 to the y values, and we are adding 1 to the x value to move it to the right. We also have something else going on. Normally, an absolute value function goes over 1 and up 1. However, in this case, we can see that if we go over 1, instead of going up 1, we actually go down 2. So that means we have both a reflection and a dilation going on for the y values. So in addition to the plus 3 for the y values, we're first going to be multiplying by negative 2. Now that we have this, we can go ahead and write the function. So we could have something here, here, and here. Inside x opposite. So if we are going from the rule to the equation or vice versa, they're opposites. So what we did was x plus 1, which means the equation is going to have x minus 1. Outside y same, so we're going to have our times negative 2 in front, and then our plus 3 tagged on the end. And there we have it. In this example, we're going to solve the equation x plus 3 equal to x squared minus 3 using the graph provided. So we can already see it graphed here, and just emphasizing that x minus 3 or x squared minus 3 is the one graphed in blue. This is the x squared minus 3. And then x plus 3 is the one there in red, which is right there. So, to find the solutions graphically are represented by intersections. That means the solutions are in 2 spots, here and here. Since this is not a system, this is just a normal equation, we only use the x values for the solutions. So the x value with the first one is negative 2. And with the second one is 3. And there we have it. So in this example, we're going to solve the inequality absolute value of x minus 1, and we have a plus 2 on the outside, is less than or equal to 4 using the graph below. So first of all, we do need to make sure to identify which function is which. The one graphed in purple here is my absolute value of x minus 1 plus 2, and the one graphed in green is the y equals 4. Now, whenever we solve equations, we look for the intersections. The intersections are here and here. However, inequalities is a little bit more complicated. So the solutions will split the graph into 3 segments. In this case, it's not always 3 segments. In this case, it is. Just like with positive, negative, and increasing, decreasing. Our first segment is from negative infinity, and I guess I had it right the first time, until we get to negative 1. The negative 1 would be included because we're focusing on a less than or equal to sign, which means the end bounds are included with the exception of the infinities. Then we have -1 to 3. And 3 to infinity. So those are the intervals. Now we just have to figure out which intervals are the correct ones. We are looking for where the absolute value of x minus 1 and then plus 2 is less than or equal to the 4. So 4 needs to be higher. So we're looking for where that green one is the higher line on each interval. On the first interval, the blue one is up higher. So we don't want the first interval. Second interval, the green one is the higher one, so this is good. And third interval, the green one once again is lower, the higher one is purple. We want green to be higher. So no for the last one, which means there's only one correct interval for the solutions. Any number from -1 to 3, including -1 and 3, will be a solution to this inequality.